Hello everyone to the 7th seminar on the Thorne calculus, a general purpose process calculus implemented as an embedded domain-specific language embedded in Isabelle Hall using higher order abstract syntax. So, where were we? We had looked at up to methods last time and before. And today I want to actually, in a sense, go back to the second subtopic and bisimilarity, and also, in a sense, the basics of label transition systems. And today I want to discuss actual transition systems. I will soon say why, or remind you why this hasn't been fully the case so far, and also weak transition systems. So what's the point here? We have seen this here, and this is about simulation systems. And what was a simulation system? This is a term invented by me. I don't know if there's some general term or some standard term in the literature. So actually, the transition system, which is the kind of normal thing, is an edge-labeled graph, which could be infinite, where the labels of the edges are actions, and the vertices are called states. They can correspond to processes of a process calculus. Then the process, or then the state, is the state that the process is in initially. And yeah, the edges are so-called transitions. And now we have this notion of bisimilarity and these underlying notions of simulation and bisimulation, and we have seen also the notions of bisimulation, simulation up to some function. And these refer to this simulation game, which I have showed you lots of times and cannot find. Now, here it is, where we have these two legs on top and on the bottom. And we say, okay, if on one side there is a transition possible, then there must be also a corresponding transition possible on the other side. And the resulting processes or states must be, again, in a certain relation that we have started with. And the thing is that, in general, you can say the original transition, the ones that is there, that this comes from another transition system, or a different transition system compared to the transition that you use to simulate this step. So, and there's a particular, or there, one case where this is so, and this is when you go to weak bisimilarity. I've mentioned this already. So in weak bisimilarity, you can just derive a so-called weak transition system from the original strong transition system, which kind of ignores certain internal communication or generally silent actions. And then you get all these notions like simulation, bisimilarity, and so on in a weak sense by just saying, okay, these are the notions for this derived weak transition system. However, reasoning with that is a bit difficult, because if you, for example, do a simulation proof, you must check that for every weak transition from P to P prime, there's a corresponding weak transition from Q to Q prime. And then you have to go through all these possible weak transitions, and there are, in a sense, more than there are original or strong transitions. However, it's possible to just consider the strong transitions, the actual transitions, because there's a general proof that we have in this framework here also, which I will show you maybe today, that says that if you only consider the strong transitions and show that these have a weak transition on the other side, then it's generally derivable that also for every weak transition, this simulation game works out. So in essence, you want this framework here instantiated for the case that your original transition is strong and your simulating transition is weak. And therefore, we had this general notion of simulation system where we permit these two transitions to be different. So the cases that we typically deal with are the following. So we have this original or strong transition that we define via some inductive definition or so. And then we derive the weak transition from it in a certain general way. And now there are different combinations of strong and weak that we could have here. So one would be that both are strong, the other one would be that both are weak, and then that the original transition is strong, the simulating transition is weak, and finally that the original one is weak and the simulating is strong. And this last one, this doesn't really play any role. I don't know if this makes any practical sense, but the other three ones, they do play a role. So this case strong, this is then the strong or the strong notion of bisimilarity that we get, strong bisimilarity, and the related notions of simulation up to, and so on. Then we have weak. This is, so to say, the beautiful, nice definition for weak bisimilarity. But then also we get this strong weak, and this is what I call here mixed, the mixed situation, so mixed strong and weak. And we get so-called mixed bisimilarity and the notion of mixed simulation, mixed bisimulation, and so on. And the point is that this notion of mixed simulation, bisimulation, and also mixed bisimilarity, that these notions are the same as their weak counterparts. So whether you have strong weak or weak doesn't play a role there. So what we do then is that we phrase certain equivalences as weak bisimulations. So we take the definition based on this situation weak, because that's, so to say, the actual intuitively right thing. But we have these generic proofs in the framework that this boils down to the same as this mixed case, the strong weak. And then when we actually reason with on the low level, where we consider the different possible transitions and see whether they can be simulated, then we typically do that we say, okay, we want to prove a weak bisimilarity. You know that this is the same as a mixed bisimilarity, and so we in the end prove the mixed bisimilarity. So we consider only strong transitions, so the actual transitions for original transition relation, and then are permitted to choose every weak transition, which includes the strong transitions, for simulating. So, and because we have this mixed case and we want to have these notions of simulation, bisimulation, and also the up to variance, and also bisimilarity for this mixed case, we have this general notion of simulation system. And the interesting thing is that all what you have seen here, including all this up to stuff, this generic part at least, that this works out for any pair of original and simulating transition that just has the same type, so refers to where the parts have the same type, so it refers to the same type of action and the same type of processes. So that's the interesting thing, that they don't have to be related in any way for this to work out. However, there are a few properties that don't work out in a general case where you need additional properties, and which is in particular work out when both are the same. And this is where we get to now the actual transition systems, where you have one transition relation, and this is just a simulation. Transition system is then just defined as a simulation system where both the original transition and the simulating transition are the same. Any questions to this point? Okay, then let's look at transition systems. So we see here.
Sorry.
Yes.
Sorry, I'm a bit late in telling you what the point was, but it took me some time to turn on my mic. So I just had maybe a recommendation for the naming of the original and the simulating transition. You might want to call one of them role model and the other the mimic. Just because, you know, when you say that this is a simulation system, it has a simulating transition, the term seems to be very overloaded. Just that.
Yeah. So the first one was what, the role model, or?
Yeah, the role model and the mimic.
Yeah. Yeah, it kind of fits the intuition, right? So, I mean, simulating transition is like mimicking. I see original is a bit blurry, and it's basically the role model. So the process that is, or the system or the behavior that is to be simulated. Thank you. So I will see if I maybe make
With pleasure.
a change here. Right. Yeah. Any other remarks or questions? So then let's look at the transition systems. So we had another locale transition system, and now it says locale transition system is simulating system applied to transition and transition. So the simulating system is this other locale. That is, a simulating system is characterized by two operations, ternary relations in essence. So they take an action and give you a relation between processes, between a source and a target process in each case. And now this transition system locale is a sublocale of the simulation system locale. This basically says the transition system is characterized by a single relation of this type called transition, and it is a simulation system where both the original and the simulating transition, or the role model and the mimic, are this transition. And you could, if you would specify axioms, which we haven't here because we don't require any conditions in these relations, then you could also add other or more axioms. So this makes it very nicely possible to model hierarchies or networks of algebraic structures. For example, you have the notion of a lattice, and then you can say, okay, now I have a bounded lattice that has two more things, a minimum and a maximum, and they must fulfill additional properties in relation to the other operations and these things. So that's very simple. Basically, it just says that transition system is a simulation system where both transition relations are the same. And then by saying that, by making this a sublocale, like a subclass, right, we inherit all the development that we have here, right? These definitions of progression relations and simulation relations and bisimulation relations and bisimilarity and all these proofs about correctness of up to and all these nice things. So we get this all for free. This is again here, this part, and this is again about notation, which we had earlier, so that we can basically have this prefix notation, like in Haskell and also in Isabelle for operators. Just put them in parentheses and have the operator inside, which you don't get automatically here because it's a ternary relation. We have this parameter for the action, so we define it ourselves with this position for the action, and then we can write an action inside these parentheses and put the ordinary parentheses outside, like here. And then we have a partial application of this transition. And this is then just a proper infix notation that's defined in terms of the prefix notation. So we inherit everything from the simulation system development. However, we don't readily get the notations. You might get them inherited. This is, I think, if your sublocale uses the same names even, I think, for the parameters. So if you have something like with this lattice thing, lattice has a meet and a join operation, and now you have this bounded lattice that gets a minimum and a maximum, and is beside the minimum and maximum, it's characterized also by meet and a join, and you have this relationship that for this to be a bounded lattice, in particular, the meet and the join must form an ordinary lattice. And then you call it call these operations the same, meet and join, and then you inherit also their notation. This is, I think, how it works. But here, the point is exactly that we don't have the same parameters or arguments because we want to have the same argument on both sides. So the notations are not inherited. So the idea is, I think, that in the former case, it's really like a specialization by adding new operations and new axioms. Here, it's a bit different. So you mess with the actual set of operations that you already had. Here it was original and simulating transition. Here's only one. So it might not be sensible to just inherit the notation in particular, since you can have several such relationships. You could have a super local and have the sublocal be an instance of the super local in two different ways. I mean, there are these things like a ring being a group in two different ways with the plus and the times. There it actually doesn't really work out because of the zero with the times, but you have such structures where, and actually we will see something similar here, I think, where you have several such relationships, which is entirely possible because unlike with type classes, locale can be instantiated the same way and or interpreted not the same way, but in different ways. And also you can have several such relationships. But I think you can have this even with type classes, right? Yeah, okay. At least with certain languages, extensions of Haskell also you can. So the bottom line of what I'm saying here is that we need to manually define these notations because they are not inherited. This is the point. So, and these things like unilateral progression, bilateral progression, and so on and so forth, these are taken from this super local simulation system. These are these things. Then notations are not inherited here, this one, and this one. But we can use this notation construct to just say assign this notation here on the right to the thing on the left. So this is if you have already defined something and you would like to establish a notation for this after the fact. And you could actually do several such notation declarations for the same thing. So you can have several alternative notations even. So for the subsection simulations and bisimulations, which corresponds to this subsection here, so it's the same structure, you basically only have the notation with notations. Everything else is inherited. For bisimilarity, you also have this notation thing, but you have a bit more. So to remind you, here we had the definition of the bisimilarity relation using this facility to make co-inductive definitions. And then we had this proof that bisimilarity is symmetric, and also that in the end, bisimilarity is the greatest bisimulation relation, and these lemmas days led to this final theorem here. Okay, and what we didn't have is something like reflexivity of bisimilarity or transitivity of bisimilarity, and that was not an accident because in general, this just doesn't hold. And why? Well, reflexivity would mean, okay, that P and P would be in bisimilarity. So we could play this bisimulation game, but it's by no means clear that we can do that. So it would mean that if we can go with P to P prime with the original transition, then we must be able to go with P now. It must be the same to P prime again, with the same action with the simulating transition. And this works only if the original transition is included in the simulating transition, but not in general. However, if both are the same, then obviously the original one is included in the other one, and then it works out. And with transitivity, we have the situation. So imagine we had a R here. We know that the P transition can be simulated by the Q transition, and the Q transition can be simulated by the R transition then. Does this mean that the P transition can be simulated by the R transition? Well, in general, no, because given a transition from P to P prime and with this original transition relation, we can simulate it with on this Q level with the simulating transition. But the next thing says, okay, if you have something here from Q to Q prime with the original transition, only then we can conclude in general that the simulating transition goes from R to R prime. So the fact that Q goes to Q prime with the simulating transition is not, in general, not of any use for us, because for the next step, we needed to be in the original transition system. So we can connect this only if the simulating transition relation is included in the original transition relation. So for reflexivity to hold, original must be in simulating, and for transitivity to hold, simulating must be in original. And obviously, both together means both relations are equal, both transition relations. And this means that in the case of plane transition systems, where they both are equal, we enjoy both properties. And we prove them here. And it's similar to this symmetry thing. So we say, first we have a rule. So this is this rule formulation where we explicitly spell out what reflexivity means. And here we just say, okay, basically bisimilarity is reflexes. So this refl P predicate takes a relation and yields true or false, depending on whether it's reflexive or not, or yields, suggests some form of computation. Of course, this is not necessarily computable. It's specified in terms of logic. And this rule formulation, this is better for reasoning often, because it directly says, so to say, what it means. And this is, so to say, the nicer formulation for kind of mathematical paper or something like this. This article-like formulation just directly says this is reflexive. So again, this P just refers to this predicate formulation of relations, in this case, the bisimilarity relation, where we formulate a relation as a function from values to bool, as opposed to the formulation as sets of pairs. Okay, reflexivity can be, it's kind of trivial to prove it. Basically, I sketched the proof with this diagram, and the point is just we apply this co-induction method, and then we get some simple goal to solve, which is solved by the blast reasoner. And here we take this rule formulation and just basically apply some trivial proof method. I think this dot meant that you just apply the standard proof method for this kind of goal, and then it probably applies some introduction rule or so, and then this is solved automatically. So this follows directly from that. So, and for transitivity, it's a bit more complicated. So originally I had some spelled out proof, but I thought, okay, that's still so trivial that I don't want to bother the read of the reasoning. So I came up with basically this proof where we apply the co-induction method, and then just we do some hacky stuff, combining proof methods of Isabel to solve the generated goals. So what does this mean? So you have this semicolon, this comma. The comma is just sequencing of proof methods. The semicolon means that, so you have this previous proof method that generates a list of sub-goals, 0, 1, or more. And it means that you apply what follows to each of the goals, of the generated sub-goals. And this is what we need here. So I got this bit from experimenting. So the auto-proof method is some proof method that combines simplification, this term rewriting, with logical reasoning, similar to BLAST. So it's a bit like a combination of SIMP and BLAST, so where these are intertwined, not just sequentially executed. And auto has the feature that it does not, like SIMP, actually, that it does not insist on proving the goal in question, but it can all leave something over so that it cannot handle anymore, some hopefully more trivial or simpler goals that you can then prove with other proof methods. And it also can work on several goals at once. This is something that I don't exploit here, but which is possible. So this ELIM is just the application of a elimination rule. I wonder whether I can make it even more fundamental. No, this does not work. So ELIM is like intro, just with elimination rules. So it applies these rules that you pass it arbitrary number of times. I think we need only one time, or maybe 2 times, I don't know. And yeah, so we could go through the details, but I don't know if this is worth it. It's maybe not too interesting, or maybe it's interesting for some, but I would like to go forward with the more general picture. So we have something similar here to above. So we say that this is a transitive relation, and this just directly follows from this rule formulation of that. So now I see that I am using here some other syntax that I don't mean to use anymore. What has happened here? It's not in the current style that I prefer now, which is this prose style. So let me phrase it like this. Okay, now it doesn't work because I now have these as extra assumptions, so I don't prove a implication, but I just prove this and get these as separate facts. And let's check. This works. Oh, great. So I'm just wondering, I think I often had line breaks in these cases. No, this to make it stylistically nice. No, here I didn't. Then I won't do it here. So good. So okay. And finally, we have this theorem that bisimilarity is an equivalence relation, and the equivalence relation is just one that is reflexive, symmetric, and transitive. And we have this egg with P predicate defined in this standard library, which captures exactly this. And we have this fact egg with PI, the introduction rule, for this predicate, and you can see what it is. And it says exactly this. Something is reflexive, symmetric, transitive, and it's an equivalence relation. So we can just use these 3 facts that we have, the reflexivity from here, the symmetry, which we have inherited from the simulation systems, which should be somewhere here. And yeah, it's here. Yep. And then transitivity, which is here. Okay. So bisimilarity is an equivalence for transition systems, not generally for simulation systems. So now for respectful functions. So to remind you, this notion of respectful functions, and we had this soundness theorem that said, okay, proofs up to context, proofs up to some function f are sound if the f is a respectful function. So this notion of shortcut progression, which is bilateral progression plus the bilateral progression for 0 steps, which is same as inclusion. And then we had this respectfulness, which is just preservation law. So f is respectful if and only if for all k and l, which are relations. We have this following property. If k shortcut progresses, this here. If fk shortcut progresses to L, then fk shortcut progresses to f of L. And then we had these numerous rules, preservation rules. So first we had these base cases like this constant bisimilarity, where independently of the k, f of k is the bisimilarity relation. This is respectful, identity is respectful, respectfulness is preserved by function composition, and the union of respectful functions is respectful, where the union can be an infinite union. So, but now we get something more. We get that chaining preserves respectfulness. So if f and g are respectful, then also the chaining of f and g is respectful. And what was that? So chaining was just the point-wise application of relation composition. So so f and g are functions that map relations from relations. And so f and g chained gives such a function that takes a k and maps it to f of k composed with f g of k. So it's point-wise relation composition. And this is an operation, is chaining, that in general does not preserve respectfulness. So why is that? So we know, of course, if f is respectful, then k progresses to L, then fk progresses to fl. If also g is respectful, then we have this situation that also gk progresses to gl. And what we must be able to conclude is that f composed with gk goes to f composed with gl. So essentially, we need what? So we have already deduced that fk shortcut progresses to fl, and gk shortcut progresses to gl. And from this, we must be able to deduce that fk composed with fl shortcut progresses to gk, no, not fl, but gk, fl gl.
Are you intentionally doing some currying here, or is it really that the implication that you have to the leftmost is really meant to be an and? So after fk, well, squiggly to fl, should the next arrow to the right not be an and, or are you doing currying?
I'm doing currying. So it's the same as saying from this and this follows that. So it's, so to say, if you use Isabel pure, you have an AND construct, but it's typically not used, but you have this curried representation. But I can also write it with the whole constructs, and it makes it maybe a bit nicer. So it's like this.
Oh, I see. So you constructed your currying. It's not that Isabel understands it automatically.
Maybe I don't understand the remark. I mean, this and the thing before is logically the same, right?
Yes. The question is, does Isabel understand that logical the sameness, or did you need to make it to understand?
I mean, I'm not sure whether I understand the question. So, I mean, here I'm writing just the term. I don't state whether it's true or not. So it's just for illustration what I mean.
Okay.
Yeah.
Okay.
And if you want to convert between the two representations, then in general you need to apply some proof methods. I don't know if you would have this kind of style if there is a pure not combinators. I mean, if there is a pure operations. If Isabel would kind of do this automatically, but at least once you switch to the whole operations, then you must use some introduction or elimination rules also for them. So it's not obvious to Isabel that these are the same, but I'm just writing this down as a term to make it written what I have just said, that it's not hanging in the air somehow. So this is what we would need to chaining, preserving respectfulness. So there's a question on the chat. Thanks, it's on the chat. You're welcome. And yeah, so, but this doesn't hold in general, and this is, I think, related to what we saw with the transitivity. I'm actually not sure how much it is related. So we have this progression, and this means that we can play some simulation games, right? So what does shortcut progression mean? It means that this thing is bilateral. Oh my goodness. This is still from the previous seminar also. Okay. So this is the general progression thing, and it can be bilateral. Then it means if we have a step on the top, we must have a step on the bottom and vice versa. And the shortcut progression, it means that we must have this for the normal transitional relations and the alternate simulating one, as well as for these zero-step translations where we go to the same process. And so now we want to have this to be true. And we know, okay, FK shortcut progresses to FL. So we can, this is FK on the left and this is FL on the left. Let me maybe write this here. So we have this. And we have also the same thing for G. No. Okay. And now we want to conclude that also the composition of these things on the left shortcut progresses to the composition of them, these things on the right. But I think it's exactly like with the transition system that this doesn't work out. It's like with the transitivity of bisimilarity. So this step for the P, maybe let me write this like this here. You see the correspondence. So from a P step, we can conclude that there's a corresponding Q step. And from a Q step, we can conclude that there's a corresponding R step. So if now P is related with Q by this FK and Q with R by the GK, then we want to have also the situation that if you make a P step, we can come up with an R step, so that you're again the situation that P and prime and R prime is in this relation FL composed with GL. But then we have again this problem that we get here a simulating step, but here we need, for this implication to be applicable, we need an original transition step. And this only works if the simulating transition is included in the original transition relation. This is what we have for transition systems where both are the same, but this is not what we have in general. Therefore, we didn't have this preservation of respectfulness by chaining in the general case. Okay, but now there's this interesting question, because with bisimilarity, we saw that in the general case, we didn't have transitivity, But also, we didn't have reflexivity, because for reflexivity to be there, we needed this opposite thing, that the original relation must be in the simulating relation, transitional relation. So we see that the fact that we don't have transitivity of bisimilarity in general corresponds to the fact that chaining doesn't preserve respectfulness in general, what we have just discussed. So now there's another such analogy. It is that the fact that bisimilarity is not reflexive in general, only in the case of transition systems, or in this case generally the original is in simulating. So the fact that bisimilar is not reflexive in general corresponds also to something about respectfulness, namely that equality is in general not respectful. So, and indeed, this is something that we have not proved for the simulation system, that equality is respectful, because we cannot. But this is something that we could prove for the transition system case. So equality being respectful would mean that if k progresses to L, then f of k progresses to f of L, but this is now, f is now the equality. No, one moment. This is not right. No. So the fact that transitivity, that bisimilarity is not transitive in general, means that chaining, which is the lifted relation composition, pointwise relation composition, that this is not respectful, or does not preserve respectfulness in general. So the fact that in general bisimilarity is not reflexive has the analog that the pointwise equality is not respectful in general. What is pointwise equality? It is the constant equality function that maps any k to just equality. Oh, yes, relation equality. No, equality relation. So we have seen this. Was it this constant bisimilarity here? Here it is. This function f, so to say, for up to methods that gets any k and maps it to bisimilarity. And if you replace now bisimilarity by equality, the constant equality function that maps any relation to the equality relation, this should not be respectful in general, but in the case of transition systems. This is the analogy to this transitivity versus chaining that we just saw. And indeed, it is not respectful in general. So respectfulness would mean that if k progresses to L, then k should progress to, no. So this is confusing. No, it's not confusing, actually. I was on the right track. So respectfulness means if k shortcut progresses to L, then f of k shortcut progresses to f of L. This is this here. You can remove that one. So this is respectfulness. And now if f is constant equality, it means, okay, if k progresses to L, then equality progresses to equality. And as you might guess, that precondition that k progresses to L is not really useful for showing that on the right-hand side. So constant equality is respectful if equality progresses, shortcut progresses to itself. And so what does this mean? So imagine we have equality on the left and on the right. And it means that P and Q are equal. I can make a step with P. I must be able to make a step with Q. And these things must be equal. And this is, of course, the case if from the fact that I can make an original step, I can conclude that I can make a simulating step, basically, if the original transition relation is included in the simulating transition relation. It's not the case in general, but it is the case when both are the same. So if both are the same, then constant equality is respectful. It is, however, not in general respectful. So now that we are here in this situation where we have transition systems and both original and simulating relation are the same, transition relation are the same, we can finally show, and for this concrete case at least, that chaining preserves respectfulness. And we can also show that constant equality is respectful, but you will discover that I haven't proved that here. And why not? Well, because we already have in the general case the fact that constant bisimilarity is respectful. This here. And now in the transition system case, where original and simulating transition relation are the same, we have this fact that bisimilarity is reflexive and transitive, but this doesn't matter here. So if you want to have a proof by bisimilarity proof by constant equality, so to say, where this f is the constant equality function, then we can just instead have the proof by constant bisimilarity. We have to show that the p prime and the q prime target processes are bisimilar. But then it works also out if they are equal, because bisimilarity is reflexive. So we don't really need this constant equality thing in practice. We just take constant bisimilarity and use the fact that bisimilarity is reflexive. So this is how we do that. But of course, considering this constant equality case a specific thing is maybe a bit instructive. It says, the fact that this is respectful and therefore sound for up to proofs, it says that if we have this, if we show that K is a, or yeah, that K is a bisimulation up to constant equality, it means that K progresses to f of K, like here. But f of K is now equality. So what we have to prove, we do such a proof up to constant equality, is that we show for every p and q that are in relation K, I can go from p to p prime with some alpha. I can go from q to some q prime with the same alpha, where the q prime is the same as p prime. So if maybe basically we get such a triangle. So if we can make a step here, then we must be able to make a step with q to the same process. And then obviously this is bisimilar, this p and this q, because it says if you can make a step with one of the guys, we can make a step with the other one, and then we are in the same process. And of course, then we can continue this bisimulation game, because if you can make a step with one of them, we can make a step with the other one of them, just make the same step. And since we are in the situation where original and simulating transition relation are the same, we can just make the same step. And this happens sometimes, that we have this kind of up to proof, up to constant equality. If you have these operations or these kind of processes which say do some action and then continue with whatever stuff, and then we might have some different processes that can execute different first actions, or that look, so to say, differently at the beginning. They make a step with the same action, and then they end in the same continuation, so to say. And then we have this situation that we land at the same process in the same state, and then just trivially we can go on with the bisimulation game. Okay, any questions?
So Wolfgang, I was wondering whether this is like the necessary condition. Is this like the most general condition that we have for the transitivity, or is it just a sufficient condition?
Well, I think the fact that the simulating transition is included in the original transition, this is probably really necessary for transitivity to hold. And that the original transition is included in the simulating transition is probably really necessary for reflexivity to hold. It's just that here we combine the two and say original and simulating transition must be the same. So each is included in the other, and then we get reflexivity and transitivity. Of course, we could have split this up and handled these two cases with the inclusion of one and the other separately. And in one case, we get reflexivity, in the other, we get transitivity. And when we combine them, say, okay, both transition relations are the same, then we get both and get an equivalence relation. This would have been possible. It's just that it didn't seem to be too useful for what we want to achieve here, because, yeah, well, actually, it's interesting because the case that originals included in simulating this is what we have in this strong weak, in this mixed case, because strong is included in weak. So you might argue it would make some sense to handle this case separately, but then again, we can prove that the mixed bisimilarity is equal to the weak bisimilarity, this weak case, and there are the original and the simulating transition relation are the same, and we get both reflexivity and transitivity this way. So it was not really super useful for us to make this structure more complex, but in a sense, it's of course nice to realize that, and would be maybe nice to have it in such a development that really there are two different conditions. One is included in the other, and the other way around. In one case, you get reflexivity, in the other one, transitivity. Does this answer your question?
Well, it's along the lines, yes, but when I had this kind of theoretical interest for a moment, but it amused me. Is this the most general condition? And your intuition of the inclusion being necessary is also what I seem to understand. But I was amused with how with investigating how correct that intuition is. And this is certainly just a theoretical interest.
Yeah, and I cannot really be sure. I mean, of course, there is this consideration like, I don't know how else I would prove that, except by just employing some inclusion condition. But I cannot be 100% sure that this is really a necessary condition. That's interesting question. I don't have a good answer to that, or no answer at all, really.
No problem. Yeah, no problem. Thank you.
I'm under the impression that those are actually equivalent. So, because I think I can prove that, for example, if constant equality is a I just forgot the name.
Yeah, a respectful function.
Yeah, exactly. I think then I can prove the inclusion.
Yeah.
And especially in the other case where we want we consider reflexivity or transitivity of yeah. I think then you can actually prove the converse also.
Yeah, I think for this equality reflexivity thing, it's probably
Yeah.
easy, because if you say, if I have a relation, a transition from P to P prime, and from Q to also the P prime, essentially. So let's say they transition to the same process R. You have this triangle under the condition that they are related by K. Yeah, then from this you want to conclude that. You just want to conclude that from this transition you get this transition without the condition that they are in K, and then maybe you need to pick a particular extreme K or so, which is of no use to you, like the K that relates all the processes or so, right? Maybe. They're wondering about the transitivity. I think this is harder. I'm wondering whether it's possible there. Maybe it is.
Yeah.
Okay. Yeah.
Transitivity seems less obvious.
Yeah. Okay, interesting question. Yeah.
So I also have a question.
Yep.
I was originally I was under the impression that the goal was to basically have a complex state machine and a more simple state machine, and then pass from that and to prove statements like this. But now you want to have both the original and the simulating systems to be the same, and I'm a bit confused by this. So, is there like a good example where you can demonstrate how you would use it?
Use what?
Use, for example, bisimilarity with those two, where you have two systems of the same, where you simulate the system with itself, basically.
The Thor calculus is an example.
Yeah, so the point is, in general, these bisimilarities where both are the same, these are kind of the intuitive ones. The intuitive thing is that your two processes that you check whether they are bisimilar, that they work with the same semantics, so to say. The notion of behavior is the same. So you first have this strong bisimilarity, the bisimilarity for the actual transition system. This is this strong case, where both the original and the simulating transition relation are the original one. This is a very rather strict one, strong one, but often you get it. For example, these basic lemmas like commutativity of parallel composition and associativity, these are all strong bisimilarities. So this is the first situation where this is useful to have both relations being the same, both being strong. And then you can derive from the original strong transition relation the weak one, which is larger. It includes the strong one. It kind of collapses, in a sense, these silent transitions. And yeah, and when you go to the weak notion of bisimilarity, weak bisimilarity, then I would say the natural way, or the most intuitive way to define it, is also via a case where both relations are the same, namely where both are weak. So you are always working in this weak transition system semantics. You can always make a bunch of silent steps along with your visible step, for example. And so the weak case is really the natural definition for the weak bisimilarity, and this is what we are using here. And the mixed case is just, so to say, for convenience of proving. So the point here is the observation that the strong weak case, that this is strong, the original is strong and the simulating is weak, that this leads to the same notion of bisimilarity as the weak case. So the mixed and the weak bisimilarity are the same. And this allows us to, if you want to prove a weak bisimilarity, which would correspond to the weak case, to say, okay, but this is the same as mixed bisimilarity, so it suffices to prove mixed bisimilarity. And then we can conduct our actual bisimilarity proof in the mixed case, where the original transition is strong, the simulating one is weak, so that we only have to consider the strong relations as given relations, original transitions. But when constructing the simulating transitions, we have the larger arsenal of what the weak transition relation gives us, so it makes our proofs simpler. I don't know if this answers your question.
So what kind of yeah, I think I'm just confused by how exactly this would be applied, but maybe I'm thinking of it in a different way. So, like, for example, what could you give an example of of these two systems in a specific case where you've used them?
So I cannot give you a good example, at least of a bisimilarity proof, because
not really of a proof, but just of
but they haven't yet been developed. But how I use it, I mean, I can show you maybe the general definition of weak bisimilarity, of the weak transition relation. Would this help?
I don't think so.
Okay. So what do you want to see?
So really, basically, a transition system. An example of a transition system where you could prove something interesting, basically. That's kind of.
Yeah, but to refer to this weak thing, you would have to see how the weak transition relation is defined, right?
I'm not even concerned about weak right now. Even just
okay.
one case.
Well, I quickly showed this parallel commutativity last time to show you basically how this co-induction method is used. Let me check this out.
Perhaps I can give some highlight here. Basically, when you are considering a weak transition, you can consider it as an over-approximation of a strong one. And if this will facilitate, for instance, proof. Let's suppose you're executing arithmetics. There's a state transition that compute arithmetics, and the weak one is just computed in an abstract way, using a lattice, for instance, saying, okay, whether you're positive or negative, doesn't care about the value, actual value of your state. Just say you're positive or you're negative. This is a weak transition for me. So you can compute a bisimilarity considering the original state where the actual computation is done, and the weak version where it's only using a lattice saying, okay, you are positive or negative, and construct this relationship showing that in any case, when you have a negative value, the weak one will say negative. When you have a positive value, the strong one will say positive. That's how I see the correlation between the original and the simulation relation.
Well, it's certainly so that the strong bisimilarity is included in the weak one, so both are equivalence relations, and the weak one generally identifies more processes or states compared to the strong.
Exactly, it's an over-approximation, but it basically facilitates proof of complex stuff. So you use this weak version to do your proof, and once you are happy with it, you show that the weak version is bisimilar to the original one, and then you know that the original will also respect the properties you've proved on the weak version. That's generally what we do.
There's no weak version
in
of a
practice.
process, so it's the relation that is weak.
Exactly.
Maybe I don't get it at the moment.
But what I'm saying that by similarity, you can show that yes, the strong and weak are in bisimilar. Okay, no problem. But you use the weak version to prove things.
But how can the strong? I'm confused.
But if properties you prove on the weak are satisfied, you know that if the strong is bisimilar to the weak, you know that the strong that includes even more complex definition will also satisfy the properties you've proved on the weak version.
No, but there are no weak versions of processes or strong versions. The bisimilarity as such can be strong or weak. So there are two different notions of bisimilarity. You have your two processes, and essentially you have two different notions of behavior. So the strong notion takes these internal communications into account and distinguishes certain behavior of different distinguishes certain processes which are not strongly bisimilar because they differ in their internal behavior. However, weak bisimilarity would relate these two processes if they only differ in their internal behavior, because the notion of weak behavior ignores the internal behavior. It only cares about the externally observable one.
Yeah. Okay. Okay.
So.
Okay. I think staring at this example, like this parallel example, long enough was very useful. Maybe I can tell you my thoughts, and then you can tell me.
Yes.
So I could, for example, have some state machine that somehow takes inputs from somewhere, does some processing on them, and then in the end does something on these inputs. But it has this feature that it can basically take many inputs at once in some arbitrary order and execute them in parallel. Now, do all of this in parallel. And so what you could then do with this bisimilarity is basically show that it doesn't really matter, like if all these parallel processes don't interfere with each other, then you could basically show that it doesn't really matter in which order, for example, they arrived, or which order they are stored in the internal state or something. And you can just pick your favorite, for example.
I don't think that's really what it is about. So I think what you are doing is you consider a single process and different inputs, and you can say, okay, for this process, it doesn't matter whether my input packets appear in this or that order. But that's not really what the bisimilarity is about, because with bisimilarity, you consider two processes, and what you want to show is that although these are different processes, the processes here this is a bit of the bad terminology. Process is the process term, the program, so to say. You have two different programs, and you want to prove that they show the same behavior. And so, for example, in these network equivalences, we had this. I don't know if it makes much sense to show the code, but maybe it's better to give you the general picture. So we have these proofs which have some holes for the low-level properties they use, but otherwise they are complete. These proofs that show that, for example, a peer-to-peer network is, in a sense, shows the same behavior than a ideal broadcasting medium. And so we have different nodes. So we had a concrete case where we had 4 nodes that were somehow interconnected via network links. And this is the kind of peer-to-peer or relaying case. So one node posts a chain or a block or some packet, for example, generally. And then it reaches its neighboring nodes, and these forwarded to their neighboring nodes, and so on. So, and as long as the network is connected, so your data will go everywhere. And now with an ideal broadcasting medium, it's just if you post, then it will reach everyone directly, not via intermediate links. And now what we we want to show that this, in a sense, is the same. And in what sense? So the key thing is here that when the relaying network relays, when node relays packets, they receive packets and then they say to the outside, hey, I have received the packet. But at the same time, they forwarded it to their neighbors. And this forwarding, so this combination, so basically this forwarding is internal. It's not observable from the outside. And therefore, these two things, relaying and broadcasting, they are not strongly bisimilar, but they are weakly bisimilar. They don't show the same behavior if you look at the internal communication also, because the broadcasting does have virtually no internal communication, doesn't have this forwarding. However, they are bisimilar in this weak sense. They are weakly bisimilar, because then you can ignore this internal communication that is involved in this forwarding. And from the outside, you just see, okay, I send a packet and it arrives everywhere. Everyone will say at some point, hi, I have received the packet. So I don't know if this makes it maybe clearer.
Yeah, that was very helpful, thanks. That's exactly the kind of example I was looking for.
Yeah. So it's that processes can be used to implement stuff, but also, if you phrase things more abstractly, to specify stuff. So in our case, it would be that we don't implement the network. We take the network as given, but we can model its behavior also with processes. It's then more for specification, and we have these different processes for different kinds of communication media, networks, broadcast, and we want to kind of show that for our purposes, it doesn't matter which one we have. The research papers use broadcast. We in reality have relaying, and in some sense they behave the same. And here we definitely need weak bisimilarity, because if you look at strong bisimilarity at the internal communication, then they do not behave the same. But taken as black boxes, so to say, they behave the same.
Okay. Yeah, thanks. That's very useful.
Great.
Sorry for interrupting so long.
No, but I think it's good to get these things clarified, because otherwise we are not on the same page for too long, and then it's difficult to put these things in context. It's very, very important, I think, that these questions get asked and answered.
I was just confused because I was originally thinking of different kinds of analysis you would do there, and then your code basically suggested that the way I was thinking wasn't correct. So I was confused for a while. But yeah.
Yeah. So coming back to what I mentioned before, so the ideal situation is where we really work for both processes that you compare, always with the same notion of behavior, either strong, where you consider the internal communication, or weak, where you don't consider it. And it's just that if you take the weak approach, where you ignore the internal communication, then you are still left with this situation that you can get any weak transition, and you must, for one of the two processes, for example, relaying or broadcasting, and you must show that it can be simulated with a weak transition of this other process. And there are much more weak transitions than strong transitions, because they do this collapsing of internal communication. And so you must consider all this collapsing also. And so you end up writing virtually the same boilerplate code every time. And this general proof that mixed and weak bisimilarity are the same does this once and for all. So you only have to consider the real individual steps, the strong steps, but then have the ability in your proofs, or the permission to use weak steps for the other. I think you must prove that if one of the two processes makes a strong step, then the other one must be able to simulate that with a weak step, which can include then additional internal communication, for example. So the case where both of these transition relations are the same, this is the normal thing. And this mixed case is just more technicality, which makes the proof of weak bisimilarity easier, because we have this statement that this mix, this strong-weak combination, leads to the same notion of bisimilarity as the weak-weak combination, which would then be the weak bisimilarity. Okay. We are almost through this transition system theory. Theory in Isabel is something like a module in Haskell. So I think we have discussed this informally already quite extensively, this fact that chaining preserves respectfulness. So it rests on this observation that once we are in the realm of transition systems and know that both the original and the simulating transition relations are the same, we have, well, this is first for shortcut progression. So that if K1 shortcut progresses to an L1 and K2 to L2, then the composition shortcut progresses to the composition. I think this corresponds kind of to what I showed here. I had this already with the FG, sorry, with the FK and the GK and the FL and the GL. You remember I had these two here, these two diagrams on top of each other, but you can play this game just with a K1 L1 and a K2 L2. It doesn't matter that this is F applied to something or G applied to something. So if you have a composition of relations on the left-hand side and a composition of relation on the right-hand side, and you know individually you have these shortcut progressions, then you have the compound shortcut progression for these relation compositions. And this is what we have here. So here in this lemma. So if we have the individual shortcut progressions, then we have these the single shortcut progression for the compositions. And from this, it follows then that respectfulness is preserved by chaining. So given that F and G are respectful, the chaining, the pointwise relation composition is respectful. And we first state what it internally means, so to say. So this is, again, this outer syntax for some Isabel pure logic, this core logic statement. So this for basically is a universal quantification, and this if says that this is a premise, so we get an implication. And we see this if we go to after this proof block, then we see what it means. It's this one here. So K progresses, shortcut progresses to L, then this shortcut progresses to that. And the K and the L have these question marks, so schematic variables, which are not fixed variables that come from somewhere, but which are universal. So they are kind of universally quantified. This is what this for K and L does. But if you write it like this, it not only looks maybe in some sense nicer, a bit more prose-like, a bit more in the style of mathematical books and papers, but also it means that the goal that we have to prove here in this proof QD block is not this thing with the implication, but it is just the conclusion, this one. This is what this thesis here refers to. This is what we want to and have to prove. And the point is that this thing, this premise, is separated from that. It's available as a local fact. It's not something that's generally true, but it's locally true in this block because we prove this only under the condition that this is true. The K and the L, they are fixed, so we can refer to them. We can say, okay, we have some arbitrary but fixed K and arbitrary but fixed L. And then we can just say, okay, from the fact that F and G are respectful, which are our assumptions in this lemma, and the fact that K progresses, shortcut progresses to L, which is our assumption here in this local statement, we have that this shortcut FK shortcut progresses to FL, and likewise for the G. This follows directly from the definition of chain. No, this follows from the definition of respectfulness. So respectful F means that from this we get this, and respectful G means that from this we get this. So, and this is something that the simplifier can figure out. You don't write simp, but simp all. This is a proof method that applies simplification to all goals, not just to one goal. Here we have two goals. Here you see this. We have this goal which uses this and. This is the conjunction in the Isabel pure logic, and it is split then into 2 sub-goals, and sim all solves the 2 sub-goals. That's very trivial. It's just application of the respectfulness definition. And then we can show the thesis, which is this, and this follows from this preservation of shortcut progression by composition, right? So from this and this here, from these 2 things, which we feed here by the then, we get that by this lemma above here, we get that fk composed with gk shortcut transitions to fl composed with gl. But if this is the case, if you have this single shortcut composition, then it means this, because fk composed with gk is just f chain g applied to k. This is how the chaining is defined, pointwise composition. And likewise on the right-hand side with L. So what we do is basically that. So we first say this unfolding. This is just application of an equation. The chain def, this is just a definition of chaining that we wrote down. It's this one here. How chaining is defined. So if we unfold using the chain definition, then this chaining here is unfolded. So if you go here, then we see what the underlying meaning is. And then, of course, this follows from that by directly applying this lemma here, relation composition shortcut progression. So we can prove that by the fact relation composition shortcut progression. And then we have proved this here. So from K progress to L, this progresses like this. And this means that f chain G is respectful. So the thesis follows by just the definition of respectfulness, which is considered by the simplifier automatically. And then we are done. Okay, regarding up to methods, there's not much to say. It's just, again, that we want to use the same notation as in the general case. So this simulation up to some function f, where the function f comes here and is written as a subscript. So this had been introduced for the general case. It's also used here. And this concludes the discussion of transition systems. So you see there's not so much here, because really the bulk, including this all this machinery for up to methods, despite the more concrete up to context, but the general machinery, which is already very powerful because you have up to bisimilarity, for example. This is all handled for the general case, where the original and simulating transition may be different and completely unrelated, actually. And surprisingly, all this machinery works out for that. And here we only really have some few additional things. I mean, this notation carrying over, this is technically the thing that has to be done. And what's really is added, the reflexivity and the transitivity of bisimilarity, from which we can conclude that bisimilarity is an equivalence, because in the general case we have already symmetry. And finally, using this auxiliary lemma, that now chaining is also respectful, which is related to transitivity, of bisimilarity. And that's it. And next time, I want to look with you at weak transition systems. That gets a bit less trivial. And then hopefully also some things that might have been unclear now will get clearer. So there we derive weak transitions from the original strong transitions. And then we establish what the weak transition system is. It's just a transition system for these weak transitions. And what the mixed transition system is, it's just a simulation system, because now both can be different, from transition and weak transition. And then we have some auxiliary stuff. And finally, we show that a weak simulation relation is the same as a mixed simulation relation. And likewise, oh, that's quite involved. And likewise, then for the bisimulation, this follows. And then in the end, we get this statement that weak bisimilarity is mixed bisimilarity, which is this central thing. And then there are some corollaries. And then there's something interesting about up to methods also. So at least some of this is topic for next week. And thank you for listening. Have a nice weekend, and bye-bye.